Without further delay, introducing the Precast Modular Block Design Manual for Gravity Walls provided by ReadyRock. Please note that this is a sponsored event and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors and pricings of products and services. And now it is my pleasure to welcome our moderator, Laura Helbling, Technical Support and Design Resource Engineer with ReadyRock. Welcome, Laura.
Hi, Robin. Thank you.
Okay.
I'm going to share my screen. Okay. Hi, guys. I'm Laura Helbling. I'm a civil engineer with ReadyRock. I also just wanted to reiterate that at the bottom of your screen, there is a chat function that is for comments only and webinar information. If you have any questions for myself or the speaker, you can put that in the question and answer section, and we will keep track of that throughout the webinar, and then any questions for the speaker will be done at the end of the presentation. We will also be sending out one PDH for attendance of this webinar, and that will be coming in an email after the finish of the webinar. So I want to start this webinar off with a poll. We want to know that what best describes the type of work you do. Is it general civil engineering, geotechnical, geology or geosciences, structural engineering, construction, architecture, or something else? We will come back to those results in a few minutes. About ReadyRock. So our company motto is changing the world in concrete ways. It's a little punny, but we genuinely believe that to our core, and we do that by three ways. The first is taking time to care. We care about our customers, their projects, and their businesses. We lead the way by providing expert support and design resources for everyone. And we never give up by finding solutions for every project, no matter how big or small. We are headquartered in Petoskey, Michigan, which is pretty much as far north as you can get in Michigan before you reach the UP. And we were established in 2000. We actually started as a heavy construction company, and there was a need for retaining wall blocks. So we thought, let's figure it out. And so we generated and manufactured forms to precast modular blocks. And so we manufacture these in Petoskey, and we distribute them to precast concrete manufacturers around the world. And here are the ReadyRock manufacturing locations around the world, and we have over 150 manufacturers worldwide that we partner with. So if you have any specific questions about ReadyRock, you can reach us at this email listed, or this is our direct line. One of our engineers will answer your call or return it if you have any questions. So before I introduce our speaker, we would like to see who is in our audience. So thank you guys for responding to the poll. And with no further wait, I am going to introduce Jamie Johnson. So Jamie started as an engineer with ReadyRock 16 years ago. He is now the Director of Innovation of Astor Brands, which is the licensing company for ReadyRock, Rosetta Hardscapes, and pole-based precast concrete products. Jamie received his bachelor's and master's degree in civil engineering from Virginia Tech, and he also wanted me to let you guys know that he is as hokey as it gets. And so now I am going to stop sharing, and Jamie is going to start his presentation.
Thank you, Laura. I sure do appreciate it. I'm trying to click just as fast as I can go here. I'm going to share my screen. So anyhow, boy, this is really exciting. Really, precast modular blocks are something that I've been involved with for quite some time. It's a type of retaining wall that I'm really passionate about. And to be honest, I was just thrilled when I saw the number of folks that registered for this webinar. It's really amazing that there's a significant number of people out there that also find this subject matter interesting. So I just want to thank you for joining. And what we want to do today is we're actually going to introduce a new book. This was one that we just completed. It's a book that I wrote with two colleagues and close friends, and it's specifically written for precast modular block retaining wall systems. It focuses on precast modular blocks. It highlights some of the unique features of precast modular blocks. It's a great tool, kind of a starting point for engineers who want to understand these types of systems. And really, in a lot of ways, it's a book I wish I would have had 20 years ago. So one of the first things I do want to get right off the bat, a driving constraint in writing this book is this is a non-proprietary book. We're covering topics, trying to dive into the engineering details of the precast modular block retaining walls and those systems. It is not specific to any particular brand that may be on the market. The concepts and the principles that we cover in the book apply to all of them. And it was really our goal to write a reference manual that engineers would be comfortable using and that they could use not just to one system exclusively, but really to this entire classification of retaining walls. Now we'll give you just a little bit of background. Now I'm sure there are several people on the webinar that are familiar with precast modular blocks or PMBs. There will probably be a few that maybe this is one of the first times you've heard the term. What is a precast modular block? Essentially, it's a great big wet cast concrete retaining wall unit. They are similar to, but in a lot of ways quite different from the smaller segmental retaining wall units or SRW units that so many folks are familiar with. Now there is an ASTM specification that's been out for 5 or 6 years now, ASTM C1776. It has a lot of information specifically defining what precast modular blocks are. It's a great resource and, like all the ASTM specs, a really good source of information. But what I wanted to do was highlight just some of the main features of precast modular blocks. First, precast modular blocks are made from a wet cast concrete. Wet cast concrete, kind of the distinction there is it's a concrete mixture that's prepared with a high enough water cement ratio that it has a measurable slump. This type of material is a very durable material. It can be a very dense concrete matrix. It's really an excellent material to make the precast modular block retaining wall units. It's really well suited. One of the next distinguishing features of precast modular blocks is they're big. They're big, heavy concrete units. Maybe some of the baby ones would start at a couple 100 pounds, but lots of the PMB units are 2,000, 3,000, 4,000 pounds or more. They are set with heavy construction equipment and generally set with fairly small size construction crews. You'll have an equipment operator, maybe a small skid steer to bring material to and from the actual construction area. And you've got a kind of a foreman on the ground who's sort of directing things and helping make sure people know where things go and just there to kind of keep the project moving along. As a result, they're really efficient. They can be installed, at fairly high production rates. Another feature of precast modular blocks is they are precast in factory controlled conditions. One of the great benefits of this is when the blocks show up at the construction site, they're ready to go in the retaining wall. You don't need to set up forms. You don't need to pour concrete on site. You don't need to wait for it to cure. Essentially, you can take the blocks right off the truck. They go into the wall and you can start building immediately. And in fact, PMBs are kind of a preferred solution for a lot of emergency repair applications because of this fact. And at the end of the day, it's not a new idea. I'm sure some of you may or may not realize, the stories of Solomon in the Bible, when he built the temple, all the blocks that went in production of the temple were prepared off-site. Same idea with precast modular blocks. It's kind of maybe an old idea come new again. Another feature with precast modular blocks is it has to do with the size of the units and that wet cast concrete. It's really an ideal material to take a lot of great shapes. And as a result, many precast modular blocks have some fairly significant face textures, maybe 4, 5, 6, 7 inches of face texture on these units. And a lot of times they're chosen specifically for their look. And one thing that's kind of unique for precast modular blocks is it's not one size, one shape, stack them up from bottom to top and that's what you've got. Precast modular blocks can come in multiple widths, multiple heights, multiple setbacks. The beauty here is it really gives engineers the opportunity to design some super efficient structures. It's really neat how they can be applied. Where are precast modular blocks used? Pretty much anywhere you need a retaining wall, there's a good chance that a precast modular block will work. I'll show you a few pictures just to kind of give you an idea, but it really could go anywhere. Here's a project. This one's near Vancouver in British Columbia. It was a road winding project, and precast modular blocks really fit the bill here. This project in the lower corner is from Wales, and it's a marina expansion project. There was a river that outlets to the Atlantic Ocean, and prefabricated modular blocks were used to expand the marina. This project is from Eastern Canada. It's actually a mechanically stabilized earth wall that uses prefabricated modular blocks as facing units. And yes, the train is supported by the wall. And you see PMBs sometimes can be used in some very intense applications. Here's a project from Kentucky. You can see precast modular blocks are often used in water applications, whether it's a channelization project or a detention pond or a retention pond. They're great big concrete units that have very clearly and well-defined engineering properties. And they're really, in a lot of ways, just the ideal unit for engineers to be able to design projects in water. And here's even one more. This one's from Missouri. We've got a parking lot on the bottom. We've got a upper level parking lot. This was a gravity wall constructed with PMB units. The upper rows incorporate a vehicle barrier. So really, you could see PMBs are used in a lot of wide variety of applications. So why did we write this book? Why are we having this webinar? Well, some of it, quite frankly, comes from my own personal experience. Been with Ready Rock for a long time and had just the privilege and pleasure of speaking with engineers really all over the world on a whole series of different types of projects. And there were some things that we've heard over and over again. One of the things is, someone would call up and say, I need a retaining wall for this product or project I've got here. I need someone who can design a Ready Rock wall for me because it's a proprietary system. And, every time I got that call, I kind of died a little bit inside, realizing that, quite frankly, this is it's kind of a general classification of retaining walls that folks with training in wall design and geotechnical and structural engineers can easily do and do well and can provide some great solutions for their projects. It doesn't have to be considered proprietary. This is engineering theory. We wanted to make it available to everyone, and so we wanted to write a non-proprietary manual that engineers could follow. Another question we got a lot of times is, well, I've got a project. I know I need a wall, but I really don't know where to start. Maybe they've designed other types of retaining walls in the past, but what do I do with these big blocks? Where do I go? How do I learn about these systems, and where can I see examples? And another reason why Nils and Clint and I decided to kind of team up and write this book. You can find information on retaining walls in just a ton of different locations. You've got soil mechanics textbooks, you've got like FHWA manuals, AASHTO bridge design specifications, or just a wealth of knowledge found all over the place. Papers written at engineering conferences or ASCE manuals. There's a ton of information scattered in a wide variety of places. What we wanted to do is we wanted to bring a lot of the concepts and theories together in one location, and have references to engineers so they know where they can go find these other documents as well, and make it easy for engineers, easily accessible to understand how to design these really fabulous walls. So that's kind of partly why we did it. What did we do? What did we put together? What did we write? Well, it's part textbook. We absolutely go in and we cover things like soil mechanics and strength of soils and earth pressure theory, loads on retaining walls and things that engineers need to consider in their designs. But we didn't stop there. We included several examples. This book is part workbook. We took multiple different precast modular block walls, and we kind of show step by step every calculation required from beginning to end to analyze stability of these walls, so that engineers can see how a lot of the theories are applied and how they can be used with prefabricated modular block walls. But again, when it comes to a good wall design, it's much more than just saying, oh, I've got a block, this block's big enough, it's not going to get pushed out of the way or tipped over. There are all the details that go into a good engineering project that really make the difference. Things like, how do I make corners, or how do I make curves, or how do I incorporate vehicle barriers in the walls? How do I handle steps and changes in grade? What do I do about utilities? All the things the details that really make a project special. We've got a whole chapter on details where we cover a lot of these topics so engineers can understand how that they're generally incorporated in PMB walls. And then, we took an opportunity and put some other stuff in as well. We've got a whole appendix on graphical solution for Coulomb earth pressure theory. If you're in the retaining wall world, maybe you're familiar with this, maybe not. But when you really start sitting down, sketching out vector diagrams, all the assumptions that are made when we're calculating forces on retaining walls, you can learn so much so fast. And so we thought, great, let's put it in the book. So there's a whole appendix in there on a graphical Coulomb solution. So that's sort of what we did and why we did it. Again, like I said, there's lots of places you can go to learn about retaining walls. This particular book was written specifically for prefabricated modular blocks. When you read it, you're going to see a lot of things in there that are similar. You've seen in lots of different locations. But there are some things that are different. And really, the differences mostly come down to the fact that you're designing great big concrete blocks. A lot of the theory is the same. The math and the equations are the same. The values that you're using are different. And this impacts everything from like calculating the ultimate bearing capacity of soils underneath the retaining wall. When you run those calculations with a great big, say 5-6 foot wide prefabricated modular block, at the base of your wall, you're going to get a different value for the ultimate bearing capacity of that soil than you would if you were analyzing maybe a small 18-inch or 24-inch wide strip footing. There are other things as well that you're going to see. One of the things that you'll see, and like I mentioned before, with PMBs, they often come in multiple different sizes, multiple different widths, different heights, different setbacks. And this truly does allow for a lot of creativity and flexibility in the design by the design engineer. At the same time, the engineers need to know, how do I account for that in my design calculations? What do I do and how would I define the back of wall? And so what we're going to do is we're going to actually spend some time in this webinar. We're going to run through an example. We're going to show you some of the things that we included in the book, and kind of just really use that as a way to give you a taste for what's there. Now, if you remember from your soil mechanics class, Coulomb earth pressure theory, there are a bunch of assumptions that are made. One of the assumptions that's made right from the beginning is that you have a straight line that's the back of your retaining wall. And then you also have uniform friction between the retained soil and the retaining wall itself. And this was just one of the assumptions that was made right at the beginning, and it's baked right into the formulas where we calculate active earth pressure coefficients. Now, when you look on the right, you can see this is just maybe an example of a PMB wall. You can see different size and width units stacked up together. Now, you can certainly envision these units, the core areas and the areas in between the units, and sometimes area behind the units are filled with stone. But you've got steps in the wall, you've got different materials. It's easy to see that the assumptions that were made for Coulomb's earth pressure calculations, they probably don't easily apply to prefabricated modular block walls. So what do we do? And it turns out there's a couple approaches that engineers use. Certainly one is found in the AASHTO bridge design specifications. Truly great reference. Engineers have been relying on these specifications for decades. Really kind of just the absolute great source to go to. And they do have a section in the bridge design specifications, section 1111, that deals with prefabricated modular walls. PMBs fall within this classification. And so there's some guidance in the bridge design specifications for analyzing these type of walls. There's also, if you go into section 3 of the AASHTO specifications, where you're calculating loads on your structures, they have a figure in there, and they show, they've got some commentary on how you can calculate earth pressure for prefabricated modular walls with irregular pressure surfaces, like we would have with different width units in the same cross section. And to see how this would apply to PMB walls, we can start with a sketch, and this might just be an example of a wall that you would see. Now, what the approach presented in the AASHTO specifications is you're going to draw a line, and it's going to be an approximate line to represent the back of the retaining wall. You start at the bottom back corner of your lowest PMB unit, and you want to draw a straight line up to the top back corner of the uppermost PMB unit. You can see the red dashed line here. And we can assume that that's going to be a good approximation. That's going to be an average back of wall that we could use when we wanted to calculate earth pressure on this wall. Now, one of the things that comes up with this is that this is a pretty good line for deciding or for calculating pressure on the wall, but we've got stepped units, and we're pretty sure that when this thing is, earth pressure is acting on it, wants to push it out of the way, wants to tip it over, there's going to be wedges of material that form, wedges of retained material that are going to actually act with the PMB units and are going to be effective as part of the wall and resisting those forces that would want to push it out of the way or turn it over. And with this approach, engineers they really need to use kind of their best engineering judgment to help kind of draw lines to signify what portions of the soil act as retained soil and what portions would form wedges that act with the PMB units. So that's one approach that's taken. It certainly gets easier with time, and as you kind of really get more familiar with these systems, kind of those engineering judgments, you can make them a little bit easier. But that's not the only approach that engineers use. And so that's not the only thing that we put in the book. We also included an approach. It's found in some German design standards, DIN 4085, just a fabulous reference. About the only negative is it's written all in German. I couldn't find an English translation, and I don't speak German. But Google Translate is amazing. Between that and the diagrams, there's just a treasure of engineering theory in this specification. And they do have a section in here that deals with earth pressure on like PMB walls with irregular or different width pressure surfaces or non-flat back of wall conditions. The approach that is found in these German standards, it's very similar to the approach that most engineers use when we're dealing with layered or stratified soils when we want to calculate forces on retaining walls. In this case, instead of having different layers into the soil, we've got different back of wall conditions. And we're going to use an example here to kind of show you how that would be applied. So this is just an example PMB wall. You can see it's made up of 4 different units, a base unit, which is wider, and then it goes to a narrower unit, and 3 units that stack to take us up to the top of the height that we want to achieve with this particular retaining wall. Well, with the skewed back of wall approach, what you want to do is you want to take each section of the wall kind of one by one, and you want to decide where the back of wall would be in the different areas. So we can start at the bottom of this wall. Usually it's easiest to start bottom up when you're defining back of wall. And here you can see we'll start to draw a red line at what we could consider to be the back of wall. And it follows the back of the lowest PMB unit. Once we get to the top of that lowest PMB unit, you can see we're going from a wider unit to a narrower unit. And again, this is where we would expect the soil wedge to form. That soil wedge is going to be very similar to what we calculate in cantilever retaining walls that have a long heel. You can calculate the angle, the failure angle that would form, that would separate kind of a wedge that acts with the retaining wall from the retained soils. And so we get this second area that follows the back of a wedge of retained soil. And then once it gets to the back of the units, we can actually, you can see we've got, 2, 3, 4 units that are going to stack up on top of each other. They've got a real small setback between them. And we really have effectively just kind of a constant back of wall in this area, similar to what you'd have with maybe an SRW wall. So what we ended up with is 3 different zones. We've got zone 1 that kind of follows that sort of constant back of wall area at the top. Zone 2 that follows the wedge that would form between the wall and the retained soils, and zone 3, which follows that lowest PMB unit. Now with the skewed back of wall approach, what we do is we're gonna look at each of these zones separately. And we would say, well, in zone 1, we know what the parameters are. We know what the conditions are. We know what the back of wall angle is. We know what the friction between the retained soil and the back of wall is. We can calculate an active earth pressure coefficient. And if the entire wall were just like zone 1, we would calculate the vertical pressure in the soil. It's just the unit weight of our soil times the depth. Then we would multiply that vertical pressure by an active earth pressure coefficient, and we could get a pressure diagram, triangular shaped pressure diagram that the active earth pressure would be acting on the retaining wall. Well, we've done that for zone 1. What we do with the skewed back of wall is we just do that for the other zones as well. So if the entire wall were like zone 2, we're going to have a different angle at the back of the wall. We're going to have probably some different angle of friction between the retaining wall and the retained soil, where you would calculate a different active earth pressure coefficient. And we're going to have the same vertical pressure diagram, again, just the unit weight times the depth. But when we use the active earth pressure coefficient from zone 2, we get a different pressure diagram. And then we do the same thing for zone 3. again, use the properties of zone 3, and we can calculate an earth pressure coefficient for that zone, and actually calculate and graph what the pressure diagram would look like. Now, with the skewed back of wall approach, what we do is we basically take the area of the pressure diagram from zone 1 and apply that in zone 1. We take the portion of the pressure diagram from zone 2 and apply that in zone 2. And we take the portion of the pressure diagram from zone 3, we apply that in zone 3. Again, almost exactly the same approach that we use when we're looking at stratified or layered soils. There's a great FHWA document, I think it's 071, that has the stratified soils approach in it. If you open up that reference and you look, you're going to find a very similar approach where they'll create a theoretical or a composite active earth pressure diagram. And now, once we have this composite diagram, all we need is the area of that diagram. The area of the pressure diagram is really going to be the force that's going to act on the retaining wall. And so, like I said, the book it's half kind of theory, half kind of textbook, and it's half examples. There's an example in the book of how to apply the skewed back of wall approach. And we're going to go through in this webinar, we're going to follow it step by step. I'm going to warn you right from the start. Fans of Douglas Adams, Hitchhiker's Guide to the Galaxy, recognize this warning. Don't panic. There's a lot of math. It's going to go really fast. You absolutely will not be able to follow every calculation. Please don't try. At the end of the webinar, if you're interested, we'll tell you how you can get a free copy of this manual. And all these calculations are in there. You can follow them at your leisure if you want. What I want you to see is kind of how the approach is made. Just sort of follow along the general procedure we're doing. And then when you go back, if you want to study it in detail, it'll make a lot of sense. So for the example in the book, we have a PMB wall. It's made up of it's a 6-foot high wall made up of 4 units. The units are 18 inches or 1.5 feet high each. And the setback, or so the bottom unit is wider than the upper 3, and the setback kind of at the back of the wall there is just under 1 foot. It's 10 7/8 inches. The retained soil in this example, we assumed a 32-degree material. It had 118 pound per cubic foot unit weight, no cohesion. And you can see how we'll apply the skewed back of wall with these properties. So the first thing we want to do is we know what kind of retained soil we got. It was given to us right in the problem description at the beginning of the problem. Normally on any of your projects, you'd have soils information that you get from your geotech report. But with the different types of soils, we can actually calculate what the angle of the wedge that would form as we're stepping from wider units to narrower units. There are formulas, again, they're available in the book. You can find them in other references as well. This particular approach is an iterative type solution. So what you'll do is you assume a value of alpha, you run the calculations, and you see. So if we started by assuming the angle alpha for this particular project or problem is 30 degrees, we can run the calculations and see we calculate a value of alpha 28.989. Okay, wasn't right. What we need to do is we need to pick a new value and we're going to iterate. So in this case, we could assume 29 degrees. We run the calculations and lo and behold, it comes back that it calculates the same value of alpha of 29 degrees. Through an iterative process, we have calculated the angle of the wedge that would form in the soil that would separate soil that would act with the retaining wall from retained soil. Measured from vertical, it's 29 degrees. If you wanted to refer to the other part of the triangle, maybe you wanted to measure it from horizontal, it's just 90 minus alpha, it's 61 degrees. Now, the geotechs in here, especially the ones that really understand Mohr circle, they're going to be thinking to themselves, hey, 61, that's interesting. 45 plus phi over 2. Oh, 45 plus phi over 2 just happens to be 61 degrees. they're very comfortable with the angle that we just calculated for this failure wedge. So once we've done that, we can actually draw what the back of wall looks like. We've got zone 1, zone 2, and zone 3 following the back of wall, the slope or the angle that follows the back of that wedge of material, and then the lowest PMB unit. The next step we do is we want to calculate what the heights of the different units are. In this particular case, it's easier to work from bottom to top. So that's what we'll do. Bottom zone, it follows just that lowest PMB unit. It's 18 inches high. When we get to the middle zone, zone 2, it's a little bit of math required, but basically we're solving the triangle, right? We're calculating the height of the triangle defined by the failure wedge that forms to form that wedge of material and the angle of the back of the wall. We do a little bit of trigonometry and we can calculate that zone is 16.87 inches high for this example. And then we can calculate the last kind of zone 1 at the top. It's basically the height of the wall, 6 feet, 72 inches, minus zones 2 and 3, 37.13 inches. So we really are starting to define all the different areas. The next thing we want to do is we want to calculate an active earth pressure coefficient for each of the different zones. This is the formula that you see just about anywhere. Any soil mechanics text is going to have Coulomb active earth pressure coefficients and formulas for them, also included in the book. But you can put in the properties of each zone and you can calculate what an active earth pressure coefficient is for those zones. For zone 1, once we put in the friction angle of the soil and the delta angle, the angle of friction between the retained soil and the wall, put in the angle of the back of the wall, we calculated active earth pressure coefficient of 0.24. If we looked at zone 2, we changed the angle of the back of the wall, probably going to change the friction angle because instead of retained soil on precast concrete, we have soil on soil interface. So we change our value of delta. We can calculate a new active earth pressure coefficient. And for zone 2, it's 0.634. We do the same thing for zone 3, 0.275. Again, I'll remind everyone, don't worry about running all the numbers. It's in the book. You can get your copy at the end of the webinar, and every single number in here is found in that book. So now we've got all the zones defined. We know what the heights are. We know what the earth pressure coefficients are. We know everything we need to be able to calculate force on the back of this retaining wall. So we start with zone 1. Just like any type of retaining wall design, we're going to calculate vertical pressure in the soil, unit weight of the soil times the depth. Then when we multiply that vertical soil by our active earth pressure coefficient, we can get the active earth pressure, the diagram that represents the active earth pressure acting on the wall. And then what we want to do is we actually want to calculate some values at some strategic locations. For zone 1, we want to know the top of zone 1, it's top of the wall. There's no pressure. There's no earth, no retained earth. At the bottom of zone 1, we can calculate what the value of the pressure is on the wall, 87.6 PSF. Then we go to zone 2, same thing. Vertical pressure in the soil stays the same. It's the unit weight times the depth. We're using the active earth pressure for zone 2. And then we'll do the same thing for zone 3. And we can actually figure out what those values are at the top and bottom of zone 3. Then we simply put them together. We get our composite active earth pressure diagram, the pressure diagram from zone 1 in zone 1, the portion of the pressure diagram from zone 2 in zone 2, and the portion of the pressure diagram from zone 3 in zone 3. And like I said before, what we need to do is just calculate the area of this composite pressure diagram. That's going to be equal to the force on the retaining wall. So we run the numbers. Zone 1, we're really looking at that red shaded portion of the pressure diagram in zone 1. We want to know what the area of that triangle is, 1/2 base times height. No problem, we can do it. Then the other thing we need to take into account is that in Coulomb earth pressure theory, we assume that the force is acting at an angle delta from perpendicular to the back of the wall. And so we can actually take that earth pressure force and we can break it into horizontal and vertical components. Again, a little bit of trigonometry. We're going to use the angles that we've already determined. And furthermore, we can actually figure out a point of application for the force from zone 1. Really what it is, it's the back of wall at the elevation of the centroid of that pressure, that portion of the pressure diagram. And so we can do the same thing with zone 2. The only difference here is instead of a triangle, it's a trapezoid. But again, we're good at math. Trapezoids don't scare us. We can calculate the area of a trapezoid, and then we can break it down. We can figure out what the horizontal components are, what the vertical components are. We can also calculate where that acts on the back of the retaining wall. And then we do the same thing for zone 3. Now, once we're done, we actually have all the area calculated. And you might be tempted to just add up, the area from zone 1 or the force from zone 1 plus the force from zone 2 plus the force from zone 3. That would actually be incorrect because we're working with force vectors here. And as every fan of Despicable Me knows, vectors have both magnitude and direction. So we can't just total them up. What we want to actually do is we want to total up all the horizontal components together. We total up all the vertical components together. And then we're going to solve for the hypotenuse of a triangle. We're going to get the square root of all the horizontal components squared plus all the vertical components squared. We're going to calculate our active earth pressure for this particular retaining wall. We can also go ahead and we can calculate where kind of a theoretical point of application is. It's just a weighted kind of like a weighted gravity calculation. We multiply the different horizontal and vertical components by the areas that we determined previously where they act. It's a weighted calculation, and we can figure out kind of a location for the overall resultant force on this retaining wall. For this particular case, it acts elevation 23.5 inches. This was a 6-foot high wall, so it's just under a third of the way up the wall, and it acts kind of back near the back of that soil wedge. So, like I say, PMB walls are pretty neat. They offer a lot of tools for engineers. Actually, there were 2 approaches to calculate earth pressure on the retaining wall that we just showed here. I guess the question is, which one's right? Which one's better? In a lot of ways, that's sort of like asking a craftsman, what hammer's better, a ball peen hammer, a claw hammer, or a sledgehammer? And of course, it's going to depend on what you're trying to do. If you're trying to drive metal stakes into some hard ground, I really don't want to use a ball peen hammer. I really want a nice sledgehammer. So again, what you want to have is the right tool for what you're trying to do. Now, we can actually do a comparison here. We did the detailed calculations for skewed back of wall. It's a very simple calculation to do the approximate back of wall. You just draw that line from the bottom lowest corner of the lowest PMB unit to the upper corner of the upper. And when you run that calculation, you can see with our skewed back of wall, we calculated 738.7 pounds a foot. If we take an approximate back of wall, it's 683.9. Skewed back of wall it's got a little bit more vertical component to the way the force acts. The approximate back of wall, and not quite as much vertical component. They're different, but they're similar. I could use either approach, and I could very easily and very comfortably design a nice PMB retaining wall that's got all the reliability, it's got all the factors of safety that I want. Now, like I said, what we're trying to do is provide tools for engineers. The more they understand these systems, the more they understand the different tools, the more they can decide what they want to do. And just like you're trying to decide what type of hammer to use, you might want to use a different approach to calculate pressure on your retaining wall with a different method depending on what you're doing. If you want a quick calculation, you're just trying to run some numbers and wrap your head around a quick solution, see what you think is going to work. The approximate back of wall is pretty easy. You can do it on a napkin. There's not a whole lot to it. As you saw, as we went through step by step, the skewed back of wall is a little more complicated. However, it's extremely well suited for computer solution. There are programs out there like the Go5 retaining wall software that have this method included in the software. So, you might choose one, you might choose the other. It's also a trade-off, right? Approximate back of wall, and I'm going to have to make some engineering judgments as to what kind of soil I want to consider acting with the retaining wall, because it's not as clearly defined. With the skewed back of wall approach, I calculated a failure wedge, and so it's much more defined. So really, they kind of both apply. They're both can be used in the right application, and they're both included in the book. And this is just one example of things that are specific to PMBs that were included in the book, and it's kind of why we wrote it in the first place. So we're kind of getting near the end of the hour here. We are going to have some time for questions. Before we do, I wanted to point out, I have mentioned several times that you can get a copy of the book if you want. Our goal was not to try and sell a bunch of books and get rich. Our goal was to put a nice resource together that engineers could use to understand PMB wall systems. There is a link that you can see on the screen. There's also this same link will be sent to you in a follow-up email along with instructions on your PDH certificates immediately following this webinar that'll be sent to everyone who registered. So really reach out anywhere, and I'm sure even just Google, you'll be able to find Precast Modular Block Design Manual Volume 1. We also have some contact information that was provided. If you want to know about different PMB systems, reach out. There are companies that make and sell these commercially. Certainly ReadyRock is one, Vertiblock, Recon. There are several out there. They all have technical staff, and I guarantee you that the folks on that staff love to talk to engineers. They love to help folks with problems and figure out how PMBs could be a great solution. Feel free to reach out. Again, you're just a Google search away from getting in touch with some really great folks. I'd love to help you. If you want to reach out to ReadyRock, they're the ones who sponsored this webinar. Again, engineering@readyrock.com or that phone number. You can go ahead, you could call, talk to Laura or Daniel or Liam. Actually, I just heard the other week that they're reviewing resumes, and that team's growing. So who knows, maybe you make the phone call and you might be talking to somebody who's already tuned into this webinar. But reach out to those folks, they will help you. If you've got questions on the manual itself, you've got questions on this presentation, this webinar, you can certainly email me at jamie@asterbrands. Love to see what I can do to help you answer your questions. So you've got that information. And then I guess, like I said, we've got a few minutes here. Laura, did we have any questions come in on the Q&A during the presentation?
Hi, Jamie. We sure did. I don't think we're going to be able to get to all of them within the hour, but we will just get started. So Lawrence Taylor asked, how is making the finished face accomplished to make it look so authentic, looking like stone?
Well, that's a great question. And actually, something I've been involved with a lot with my role currently in innovation is some of the new products. So it's not just PMBs, but lots of different precast products. For the walls themselves, a lot of manufacturers will start with a stone look that they want. And because these are precast products, they can actually shape the mold. It would go in a form that you would use to cast these things. And so if you're gonna start with rock as your target of what you're trying to do, you can make that look incredibly lifelike. And then with the molds, when you pour the concrete in, it takes the shape of that mold. Most PMBs are poured in molds that are partly steel, and usually there's some sort of rubber or polyurethane type mold that really forms some very dramatic face textures.
Awesome. Okay. Tim Hess asked, on waterway applications, are there special considerations for dealing with freeze, thaw, and ice conditions?
Absolutely. Water and retaining walls generally don't play well together. But again, what you want to do is you want to engineer the proper solution. A lot of walls near water incorporate features like lots of extra, very coarse drain stone, usually poorly graded, larger rock behind those structures themselves. A lot of times you may have extra drains in there as well. And if you're in an area where you've got some soils that are going to be really susceptible to the frost or freeze thaw, you might be over excavating and getting those out of the way. That's not a PMB requirement. That's a retaining wall requirement in general. If you've got those soils, they need to be engineered, and you're going to need to make sure that you've got stuff in place to be able to safely handle that water and handle any freeze or thaw conditions.
Awesome. Christian Jerez said, how is PMB performance with earthquake loads?
Well, PMBs are very similar to segmental retaining walls in a lot of ways. They're discrete units. So you put a block down and you set one next to it in rows. And then you can come in, you backfill, and you set the next row of units on. There's inherently some flexibility in this wall system. So as long as it's properly designed that you're going to be able to handle basically the heavy loads that are thrown at your retaining wall from whatever design value you're using for your seismic load that's going to be on it. As long as it's designed, big enough to be able to stand up and it just doesn't fall over doing the shaking, the fact that it's segmental in nature, they can flex a little bit. They can move a little bit while the ground's shaking. The earthquake ends and your wall pretty much is right back where it started. You don't have to worry about major structural cracks taking away the structural capacity of the wall. Segmental walls do really well. And in super high seismic areas, if you incorporate PMBs with other types of maybe geosynthetic ground reinforcement, like in a mechanically stabilized earth wall, now you've really got something special.
Okay. Is there an example in the manual with a slope above the wall and or surcharge loads, both uniform and strip loads?
Yes, absolutely. Trying to think if we had a slope in one of the design calculations. We may or may not have. I know we have different live loads. We also have regular slopes. We have crest slopes, so kind of a broken crest slope, and we have strip surcharge loads in the textbook portion of the manual, and also in that graphic Coulomb appendix with the graphical Coulomb solution there. So there's multiple areas in the book where it refers to different types of top of wall conditions, whether it's slopes or surcharge loading. There's a lot there. And like I say, there's also plenty of folks that'd be happy to help you out. You want to reach out to any of the PMB manufacturers, their technical staff, send an email. There's plenty of folks that want to help.
Great. Does the manual address global stability of PMB walls? I have an application where a steep slope is at the toe, wondering about applicability of these systems for that type of a condition.
The manual does address it. If you run global stability calculations, that's where you want to, run those Bishop circles or, maybe use one of the other kind of overall stability methods, maybe a 2 or a 3-part wedge. You'll get a project assigned to you in grad school, and then you're going to spend most of the weekend running that calculation by hand. When you get in practice, we almost exclusively use computers to solve those problems. So we do cover it. We discuss what it is. We show results, but the solutions are really not hand calculations. They're computer solved for most practical, design firms and design offices. But there are examples in there. Now, when you have a slope on the bottom of your wall, what you need to do is certainly you're addressing that. You're addressing the overall slope stability. So it's going to go beyond just the stability of the retaining wall itself. And you're really starting to zoom out a little bit. You're taking a bigger look. And what you want to do is you want to see what kind of options you have. If you do have a failure surface that would form fairly close to the retaining wall, and you don't have enough factor of safety that you've got the reliability you want, you've got options. You could start your wall deeper, bury your wall deeper. You might need to incorporate some type of either soil reinforcement or anchors, because again, you're not dealing with just the wall itself. You're actually dealing with more an overall slope stability issue. Also, there are cases if you've got steep slopes on top or bottom, maybe you start the wall further down the slope if you can, or on top of the wall, maybe it goes up a little bit higher. When you start running the design calculations, what you're going to do is you're going to find that sweet spot. Again, that's what we'd like to do as engineers, right? We want to figure out what's the best configuration of retaining wall heights. Sometimes a little bit taller wall section, a little bit lower force on the wall, a little bit better global stability, and that's what you're looking for. It's a complex problem. The other thing that you want to do for sure is make sure you're working with a geotech engineer that really knows their stuff. Global stability is not something you want to take lightly. It really should be addressed in every retaining wall design.
Agreed. So we've had a couple people ask this question. What is the maximum recommended height for PMBs?
That's a great question. And I can tell you that gravity walls, really kind of any retaining wall, especially gravity walls, it's usually some ratio between how wide your retaining wall is, and especially the base of your retaining wall, to what the maximum height that you can retain. So some of it will depend on what unit you pick. There are PMB units out there that are as narrow as maybe 28 inches wide. And in that case, you might be maxing out at somewhere around 6 feet or so. I don't know. You run the numbers and see what soils you're in. But there are PMB units that, Ready Rock goes up to 8 feet wide. If you get into the Recon, I think they've got some even bigger units. So the wider you go, the taller you can go. Also depends a lot on your soil conditions. I know there are definitely gravity walls in the 20 plus foot range. And then beyond that, there are options to build taller walls if you use some kind of soil reinforcement or soil anchor system in combination with the PMB units as you're facing. That we have PMB walls that are 50 feet tall. There's a couple I know, very closely was involved with at a rock crusher quarry, 50 feet tall, and those giant off-road haul trucks that are bringing great big rock quarries to a crusher. They're unloading at the top of the wall. So you've got trucks their design loaded weight is almost 1/3 of a million pounds on top of a 50-foot tall PMB wall. Obviously, that's not just something you just stack up some blocks and hope. Your engineers are using their sharp pencils and they're calculating, designing MSE structures, and so PMBs are really, really flexible. They provide a lot of different possibilities to solve real world problems, and depends on what you're doing. Depends on the numbers you're putting together. You might see PMB walls from just a couple of feet all the way up to 50 feet or more.
Great. I think we have time for probably one more question. And it is, what is the standard to follow for getting enough geotechnical tests and bores done for a length of wall?
That's an excellent question. And the first part of that answer is absolutely. You have to test your soil. You need to know what you're designing. If you don't test your soil, you're just guessing. And unless you're just super lucky, you could guess conservatively and maybe have some lower strength properties of your soil that you use. And it turns out you've got a wall that you designed that maybe doesn't have the reliability you want, which is bad. We don't like that. It's almost worse in a way when you're overly conservative in your soil estimates, and you design a wall that's much beefier than you need. You're spending more money. As engineers, it's also our responsibility not to come up with the solution that will never fail, but to come up with the best solution for our customers that we can. And certainly economics are a consideration. So soil investigation, absolutely. I wouldn't design a wall without it. Just simply wouldn't do it. May run a quick calc to see where I think the wall solution would look like, but you got to have soil specific to your project site. We do have a chapter in the book. It's that is best practices. There's some recommendations in there. It has to do with the size of the project, but you certainly need a couple of soil borings for sure, and you need more soil borings as the wall gets larger. Also, when you're dealing with slopes, you want to make sure that you're going deep enough and you're getting the information really that you need to quantify the soils that you're designing in. And so you'll find some information and some recommendations, largely built on the kind of standard of practice in the industry today, kind of in that best practices chapter.
Great. Okay, so I have a couple things to announce. I wanted to let everybody know that the URL for the link to download the design guide is case sensitive. So if you copy and paste the link on the slide, or there are links in the chat, that should take you there. If you are still having issues, we will be sending out a follow-up email with the PDH for attending the webinar, and that will also have a link to the PMB design manual in that email at that time too.
Okay. And Laura, it sounds like we're kind of over time here. We maybe didn't get all the questions, but as I understand it, that chat's going to still be available to us, and we'll try and respond, by follow up with email or phone call, depending on what's appropriate with the folks that have sent in questions.
Yep, that's correct. We unfortunately couldn't get to everybody's questions, but we will follow up as soon as we can.
It looks like you're getting lots of applauses.
Yes.
You did a great job. Thank you, Jamie, as well as Laura and Madeline and Daniel for this valuable presentation, their dedication to ASCE and the civil engineering profession. And thank you, Ready Rock, for sponsoring this event. And a tremendous thank you to all the attendees that joined us today. We hope everyone stays well and has a good rest of your day. Goodbye, everyone.
Thank you. Bye everybody.
Thank you.